We talked a little bit in the last lecture about how to describe displacement, velocity, and acceleration in 2 and 3 dimensions. And now we're going to talk about a very specific type of two-dimensional motion called projectile motion. We need to define a projectile as we get started here. So a projectile is a particle that starts with an initial velocity, but the acceleration is always free fall acceleration. The initial velocity can be up, down, zero, horizontal. It doesn't really matter what that initial velocity is. What matters is that acceleration is always negative 9.8 meters per second squared down. An object that is thrown upwards is still a projectile. It has an initial velocity and it is in free fall. We don't think about it being in free fall when it's still moving up, but it is accelerating at negative 9.8 meters per second squared that entire time. So it is, by physical definitions, in free fall. When we analyze projectile motion, the horizontal motion and the vertical motion are independent. We said the acceleration is always free fall acceleration. So the acceleration is vertical only, and there's no acceleration in the horizontal. We don't have to think about what's changing in the vertical to affect the horizontal. And this is really true of motion in general. When we think about things that are at 90 degrees, moving something vertically doesn't affect its horizontal position. Moving something horizontally doesn't affect its vertical position. So, a couple examples of projectiles. We have the pumpkin from Pumpkin Chunkin'. If you've never heard of that, people build a large trebuchet, kind of like a catapult, and launch pumpkins in a competition. So the pumpkin, once it leaves the launcher, is a projectile. When it's being thrown, it's not a projectile because it's accelerating in some form other than free fall acceleration. When an apple falls from the tree, like Newton's apple falling from the tree, it is a projectile. Its initial velocity is zero because it just drops from the tree, but its acceleration is always free fall acceleration. All types of cannonballs are projectiles. Here we have one being launched by the Navy. Again, while it is in the tube here and being launched, it's not yet a projectile because it's accelerating by something other than gravity. Once it leaves, though, and it is launched, it becomes a projectile. It may be moving up, it may be moving very rapidly in that direction, but its acceleration is free fall acceleration. Same thing for a human cannonball or a human doing a cannonball into a pool. What about this? This is the launch of the Space Shuttle Atlantis. It was a picture taken at Kennedy Space Center in 2011, and we see the shuttle with its rockets burning, taking off. We said that things can be moving upwards and still be projectiles, but this is not a projectile at this point. It is not a projectile because its acceleration is not free fall acceleration. It is being pushed upwards by the rockets. Those rockets are accelerating it up in a way that is not consistent with free fall acceleration. So if I have launched a model rocket and the engines are still burning and they're making it go faster, moving upwards, so there must be some acceleration going up, that's not free fall acceleration. So how do we describe projectile motion? If we know the initial velocity, which is shown here as v sub 0, we can resolve that vector and we could get v sub 0 x and v sub 0 y. What they've done in this image is take the same projectile. We see the projectile moves upwards first and then back down, and they've resolved the x and y component of velocity at any time. You'll also notice that there's a theta 0 here. Theta is not consistent through the entire path, so we need to be careful when we talk about angles with projectile motion to be sure we talk about theta 0 or theta at some time t. So we know that that initial velocity vector would be v sub 0 x I hat plus v sub 0 y j hat. We could find it using cosine and sine. Because the vertical and horizontal components are independent, we can break the entire motion up into two separate one-dimensional problems. So we can find v sub 0 x and then find v sub x at every point along this path through time, and then we can separately find v sub 0 y and v sub y at every point along this path. One thing I want you to notice as we look at this is here at the top of the projectile motion, v sub y is 0. We learned that some when we did free fall, that if an object is traveling upwards first, at some point that velocity has to equal to 0 before it starts to come back down. So we have a positive velocity, and if that velocity becomes negative, it has to equal to 0. When we talk about projectiles, we've added in this horizontal motion. We see that the total velocity is not 0. At that very top point, the projectile is still moving horizontally, but the y component is 0. Part of why we see that it doesn't become 0 is that there's no acceleration in the x direction. So v sub x at any time is also equal to v sub 0 x. If we take one of our constant acceleration equations to try to find position, so we have displacement equals v sub 0 xt plus 1/2 at squared. We said that a is 0 because there's no acceleration in the horizontal, so we can always find the position by v sub 0 x times t. We know that v sub 0 x is equal to the initial velocity times the cosine theta sub 0, which is that initial angle. So to find the position at any time t, we use this displacement equals the initial velocity times the cosine of the initial angle times time. When we think about the vertical motion, it gets a little bit more complicated because we said that this is free fall acceleration, which means there is acceleration in the vertical. So what we have here at the top are two of our constant acceleration equations just rewritten in the vertical dimension and using g as the acceleration. So taking a look at this, we see that we've replaced our x minus x sub 0, how we've typically expressed displacement, with y minus y sub 0, just showing that we're talking about the vertical. So we're talking about a vertical displacement. We also have this negative sign here before what would be plus 1/2 at squared. It's negative because our acceleration is in the negative direction. Our acceleration is g, which has a value of 9.8 meters per second squared. So we have the negative sign and g to represent that free fall acceleration of negative 9.8 meters per second squared. We see that negative g repeated here in the second equation. If we combine these two equations, and I'm not going to step through the math of combining these, I'm happy to do that if anyone wants to see it, but I found most students would really rather not see all of it, so I'm not going to step through it. But if we were, we get this equation here at the bottom, which will let us find the velocity in the y direction for any position. And really, when I say position, typically I mean displacement, because if we let our y sub 0 be 0, our displacement is going to be the same thing as our position at any time. A couple things to note here. We see our g here again and our negative sign again, where that would normally be negative 2a in a sort of traditional constant acceleration equation. We also see that we've replaced our initial v with v sub 0 times the sine of theta sub 0. So we just have the y component of the initial velocity. We don't want to solve these problems using the entire initial velocity because, again, we've split our entire projectile motion problem into two problems. So we have a horizontal problem and a vertical problem that will then combine at the end. Or we may need to combine at some point along the way, but we're combining our problems. We're treating these two motions as independent because that's how they function. So we want to just look at the y component of that initial velocity. And again, we see that down here as well. So your first conceptual question dealing with projectile motion, a stone is thrown horizontally. So the initial velocity is going to be just in the x direction. And then it follows the path x, y, z shown here. You want to answer what the direction of the acceleration of the stone at point y is.